We are now in Section 1.4, the final section of Domain 1 of the CompTIA Security Plus exam. Section 1.4 focuses on explaining the importance of using appropriate cryptographic solutions. So what are cryptographic solutions? Cryptographic solutions are security methods used to protect data by converting it into a secure format, ensuring that only authorized users can access or understand the information. In this section, we will cover key cryptographic solutions, including public key infrastructure, encryption, cryptographic tools, obfuscation, hashing, salting, digital signatures, key stretching, blockchain, open public ledgers, and certificates. Let us get started with the first cryptographic solution, public key infrastructure, also known as PKI. PKI is a framework that uses cryptographic keys to secure communication, protect data, and verify identities. PKI is built around three key elements: the public key, the private key, and key escrow. PKI works by using a pair of cryptographic keys along with a secure management process. The public key is shared openly and is used to encrypt data or verify digital signatures. It allows others to securely communicate with the key owner. The private key is kept secret and is used to decrypt data or create digital signatures. It proves ownership and must be protected at all times. Key escrow is a secure storage method that allows trusted third parties to recover encryption keys if needed. This supports business continuity, compliance, and lawful access when private keys are lost or unavailable. Together, these elements allow PKI to provide confidentiality, integrity, authentication, and non-repudiation. The next cryptographic solution is encryption. Encryption protects data by converting it into an unreadable format so that only authorized users with the correct key can access it. The level of encryption determines how much data is protected and where it is applied. These are referred to as encryption levels. Encryption levels include full disk encryption, which protects all data on a storage device, including the operating system and system files. Partition encryption, which protects a specific section of a disk rather than the entire drive. File encryption, which protects individual files and allows selective data protection. Volume encryption, which protects a logical storage volume. Database encryption, which protects data stored within databases. Record encryption, which protects individual records or rows within a database. In addition to encryption levels, encryption is also used to protect data while it is being transmitted. This is known as transport or communication encryption, and it protects data in transit from interception or eavesdropping. Encryption can be implemented using two main methods: symmetric encryption and asymmetric encryption. Symmetric encryption uses a single shared key for both encryption and decryption and is faster, making it suitable for encrypting large amounts of data. Asymmetric encryption uses a pair of keys, a public key and a private key, and is commonly used for secure key exchange and digital certificates. To securely share encryption keys, encryption relies on key exchange mechanisms, which allow keys to be transferred safely between parties. Encryption is based on mathematical algorithms, and its strength depends on the algorithm used. Another important factor is key length. Longer keys provide stronger protection, but may impact performance. Another important cryptographic solution involves the use of cryptographic tools. These tools are used to securely generate, store, protect, and manage cryptographic keys and sensitive operations. Common cryptographic tools include Trusted Platform Module, TPM, a hardware-based security component that securely stores cryptographic keys and supports secure boot and device integrity. Hardware Security Module, HSM, a dedicated hardware device used to perform cryptographic operations and securely manage keys, often used in enterprise environments. Key Management System, KMS, a centralized system used to create, store, rotate, revoke, and manage cryptographic keys throughout their lifecycle. Secure Enclave, an isolated and protected area within a processor that handles sensitive data and cryptographic operations separately from the main system. The next cryptographic solution is obfuscation. Obfuscation is a technique used to make data, code, or information difficult to understand or interpret by unauthorized users. Its goal is not to encrypt data, but to hide its meaning and reduce readability in order to slow down or deter attackers. Obfuscation is commonly used to protect source code, intellectual property, and sensitive information from reverse engineering or casual analysis. Common obfuscation techniques include steganography, hides data within another file, such as an image, audio, or video, so that the existence of the data is concealed. Tokenization replaces sensitive data with a non-sensitive placeholder called a token, while the original data is stored securely elsewhere. Data masking obscures sensitive data by replacing it with altered or partial values, often used in testing or training environments. It is important to understand that obfuscation does not replace encryption. It is used to reduce exposure and visibility, not to provide strong cryptographic protection. Other cryptographic solutions include the following: hashing. Hashing is a one-way process that converts data into a fixed length value to ensure data integrity. The original data cannot be reconstructed from the hash. Salting adds random data to input values before hashing to prevent attacks such as rainbow table attacks. Digital signatures. Digital signatures use cryptography to verify the authenticity, integrity, and non-repudiation of a message or document. Key stretching. Key stretching strengthens weak passwords by increasing the time and effort required to derive cryptographic keys. Blockchain is a distributed and immutable ledger that records transactions securely across multiple systems. Open public ledger. An open public ledger allows transactions to be publicly visible and verifiable while maintaining integrity through cryptographic techniques. Certificates rely on several supporting components and processes to function properly, including certificate authorities, trusted organizations that issue and digitally sign certificates to verify identities, certificate revocation lists, CRLs, lists of certificates that have been revoked and are no longer trusted, Online Certificate Status Protocol, OCSP, a protocol used to check the real-time status of a certificate, self-signed certificates, certificates signed by the same entity they identify, often used in testing or internal environments, third-party certificates, certificates issued by a trusted external certificate authority. Root of trust. The foundation of trust in a certificate chain, typically based on a trusted root certificate authority. Certificate signing request, CSR generation. The process of creating a request for a digital certificate that is sent to a certificate authority. Wildcard certificates, certificates that secure a domain and its subdomains. Together, these components and processes allow certificates to establish trust, verify identities, and support secure communication. This completes Domain 1 of the CompTIA Security plus SY0-701 exam. In this domain, we covered foundational security concepts, security architecture, and cryptographic solutions. Next, we will move into Domain 2, titled Threats, Vulnerabilities, and Mitigations. See you there.